if you are coming from other backgrounds, if you are coming from technical engineering background or anything like this, and if you miss some point that you haven't seen before, if you think that you have to get more resources, get this book. Okay? I'm not saying that buy it, you can borrow it from the library, make it confidential. PDF is out there, you know, it's illegal, but you can get PDF from your friends. Also, there are few chapters over here, chapter 2, 3, 4, 5, and 9, 10, 11. Chapter 2, 3, 4, 5, sorry, 6, and 9, 10, 11. We have covered all these chapters so far. We have gone through normalization, we have gone through the ERD, we have gone through query processing, we have gone through query optimization. We are talking about query optimization. So this book is very large and very explanative, but it's a very good book, and many people are, many universities are studying this book, and this is the textbook of many places. So just go over the, you have Thanksgiving vacation, you know, holidays, and I know that besides Turkey, you love to read database books, so it's very helpful. There will be another project. I know that you have other projects in this course. The next project is Java programming. Okay. The project is implementation of B+3. Okay. The project, Professor Mahmoud told me that since people are coming from different backgrounds, in order to make sure that everyone learns how to write a good Java program, and since you are currently in the computer science program and you're expected to know how to write programs at the end, you need to learn at least one imperative programming languages. And also, implementation of B+3 will help you to understand what B+3 is. And B+3 is very important to understand what indexes is, how queries are processed, and have a good understanding and feeling about database internals. So you have to implement this. Yes, it is also recommended by Professor Mahmoud, and he's my boss, and definitely you have to do that. So, but I made the project as simple as possible for you. What does it mean? It means that I created currently Eclipse project. I have the whole implementation. Okay, I removed some part of the implementation. I'm just asking you to complete those classes. Okay, as you are not starting from scratch. You are not starting, and the B+3 is just storing and retrieving integers, not the strings. You are not comparing strings and anything like that. So let me find it. Project. Oh, yeah. So how many people are okay with Java programming out of this class? Right. Okay. So the project is very interesting. I will just go over. So the project has a few classes. One of the main classes you have to change is node, leaf node, and tree node. Okay. So leaf node is a basically, I guess it's a abstract class, and the rest of the classes are concrete classes you have to implement. I have already put 2 test files in the project directory, but do not rely, make sure that your program is working properly. Do not rely on not responding. I forgot to record. I see that everyone is excited about the project 2, right?
Sure.
Everyone? Okay. So what you need to do is you need to open Eclipse and also go to, I will post the project on Canvas, the not completed project, and what you're supposed to do is you have to go to import, then, sorry, it's better to go to create the Java project. Where was the option for importing? Okay, you have to go to import, then existing project into workspace, then you have to open this dialog, then you have to select the archive file. I will post an archive file on Canvas, then you have to go and find the archive file. So what was it? It's the archive file is, for example, in my computer is University of Bridgeport, courses, DB, project. This is the solution. So I'm not opening content of files in front of you, don't worry. So if you open the file, the solution, there are a few packages. One package is for exception. The other package is for B+3 node, and the other package is B+3. The B+3 package contains this B+3 Java, which is the whole tree in a class. There is a main executor.
It's not visible.
Also make it full screen.
Small.
Full screen.
It's very small, unfortunately. If I change the resolution of my
Isn't there like a magnifier utility you use to magnify part of your screen?
is there a magnifier over here?
Yes, you can go to Cortana.
Where is the magnifier?
Cortana section.
Where? Really?
Oh.
Oh. Oh, that's great. So I haven't worked with this magnifier yet.
There should be some with the panel screen and
Okay, so if I click on this, if I move this, lens. Okay, so probably this is more difficult than what was it? How can I get out of this magnifier?
Just
Exit.
press control and just can't move around.
This minimize this and do
Oh, maybe, how can I get out of this?
Control F4.
Okay. Control F4.
No, click on that magnifier.
Node 3 has 3 classes. Here you see that data node, leaf node, and node. Okay, so data node is node. Sorry, data node, leaf node, node and tree node. So data node is the place that you are keeping the data. Leaf node and tree nodes are those nodes. I guess data node is an abstract class, is it? I'm not sure. Okay, so data node is the place that you are keeping the data, and basically this is the only node that you have single value data. So the leaf node is the node in the leaf of the tree. Tree node is a tree node that is not leaf, and node is an abstract class. Yes, node is an abstract class. So this is a solution file. You don't see any error, but when I upload the project, then when you open the project, since I removed some part of the project, then you will see errors. So don't worry about this, and you have to see errors and you have to resolve those errors. And I have one exception over here. If you complete this B+3 with different models, you'll get extra points. Okay, the project has 10 points, but if you complete it with, for example, distributed data with B+3, then we will get 5 points extra, right? So do as much as you can, do your best, and definitely you can get a good result. And as Professor Mahmoud mentioned, this is very important to understand the concept of programming. Also, from database point of view, it's very important to understand the concept of indexes. Okay, so this is the project that I have to explain. Do we need to discuss about our previous quizzes or not? No? Okay, let's go to the lectures. So we learned about rules, and we talked about these rules. So this is one example. Did we have this example or not? No.
We didn't
So
talk about
suppose that you have R and S, and you have 3 attributes. C2 is in R, C3 happens in S, and C1 is common attribute between these two relationships. If you want to compute this expression, what are you doing? How you apply those rules, the rules that we learned last week. How can you apply those rules? First of all, there was a rule over here when you have conjunction of conditions, then you have to translate this conjunction to consecutive selections, right? So if I apply this to the first expression, then we will see that we will have 3 selections. The last selection is selecting C3. The last selection is using D3, sorry, the last selection here, select the last column. So what else? You need to help me? I don't know. So if I go back, there is a rule over here which says that we can use this C2 inside of the Cartesian product, right? Here, C2 is a part of ATTR, okay? So then we can move C2 inside of the ATTR, right? Sorry, no, it was not correct. So. Which rule I am applying? Second rule, okay. I'm putting C2 inside of the or C3. So I'm selecting C3, enforcing C3 on S. Then same thing, enforcing C2 on R. Now this is left, right? 2 relationships to select. One is selecting based on condition 2, C2. The other one is selecting based on condition 3. And there is a common condition on the Cartesian product. The common attribute, condition on common attribute on the Cartesian product. So what we are doing is, we are using what? Natural join we can use natural join. Apply which rule? We are changing Cartesian product to natural join, okay? And then we compute the rest of the query. So here is another example. Suppose that you have this query. Select professor name from tables professor and table teaching, okay? And the condition is here you need to make sure that professor ID in the ID column in table professor is equal to professor ID in the teaching table. Moreover, you need to select based on department IDs, yes, and a semester, okay? So this is similar to the example I showed you in the previous slide. Suppose that R is the table professor, S is table teaching, C2 is condition on professor table, C3 is a condition on teaching table, and C1 is a common condition. Okay? So, based on what we saw in the previous slide, we can convert this select query, regardless of P name. Suppose that you are selecting the star. The whole query can be planned as this relational algebra expression, right? The whole query can be planned as this. If you do not have this column and instead you have a star, then this will be the equivalent relational algebra expression. So then from that equivalent relational algebra expression you need to get name. So can I move this projection into these parentheses? Can I move this projection into these parentheses? Can I enforce this name? Because we are looking just for the professor name. And we learned that if we apply projection as soon as possible, then the temporary tables will be smaller, right? So can I move this p name to these parentheses, to any of these parentheses?
Yes,
Why, Peter?
because it's all we care about from the professor table.
So if I move this p to before this professor, is that okay?
No,
Why?
it will get only fetch only one column, that is name. So where will
And
you
this
put
is
it?
not valid. So
Then you can't come.
semantically you cannot move it. Because if you move this projection into this parenthesis, if you move this projection over here, then what happens is the result of this table will be just one column, which is name, as Paninja told. Then this join cannot happen at all.
Department ID.
Okay, so you are changing this P name to P name and department ID, right? And also professor ID. Because professor ID is required for this join. You see, the join happens on the ID and professor ID. The professor ID and T professor ID. So you also need one more column. So, if we can manipulate this query and revise it in order to make it more efficient, but it is not equivalent if you move it, all right? But the result will be same if we choose just these we project just these 3 columns. So, okay, now we want to estimate the cost. So we want to decide which if I go back, this is the execution plan. This execution plan shows that first compute this natural join between teaching and professor based on ID and professor ID is equal. Then select from these 2 conditions and then project the name. Right? This is the execution plan. Is that okay? Is that clear? The execution plan. You have these 2 tables. First you compute this natural join here, this parenthesis, the most inner parentheses, then you go for this select, you compute the select, then you project the name. So now I will give you some dimensions about the tables. Suppose that professor table has 200 pages, 1,000 rows, and 50 departments. Okay, and these are the indexes. We have a clustered index to level B+3 based on department ID and hash on ID. Okay, and you have a teaching table which has 1,000 pages, 10,000 rows, 4 semesters, just 4 semesters. Okay, and clustered It has a cluster 2 level B plus 3 index on semester and hash on professor ID. Okay? So, consider the previous execution plan. So, is that a good plan for this specification? Remember our discussions about indexes. First of all, this is a very dumb index. 4 semesters. You have a cluster 2 level B plus 3. Right? Isn't it? It's a very stupid index. Right? So, what about the rest of the project? The rest of it? We have B plus 3 index based on the department. So, what do you think about this execution plan with this? Do you have any approximation how you execute this? First of all, suppose you have hash index on professor ID and ID. Okay, what was the first operation? Natural join. On what? On ID and professor ID. So what you are doing is, what kind of join you will use? Query processing. Last link. What kind of join you are using?
Block nested.
What?
Block nested.
Why block nested?
Because
You have hash already.
that is the only one to reduce the time taken.
No, hash join is also very efficient. How do you say that? How do you say that? So, what? Okay, so you had the should I show the answer? So just explain what kind of approach you are taking. Suppose that you haven't seen anything over there. Come on, you read about these indexes last week. You were going through this. Start the discussion. We want to have a discussion. Any opposition? In favor? Fast?
What's the motion?
Should we go through? Nobody wants to add anything to what you were told? So suppose that we are running the first plan. As Shweta told, we will have block nested loops. Okay. What is the cost of the block nested loops for this natural join? What is the cost of the block can set loops. What was the plan? Which table is smaller?
Professor.
So which one should be the outer loop? Professor.
No, smaller.
Smaller one, because what was the cost?
200.
R1 plus beta 1, beta R plus beta R multiplied to beta S, which if beta R is the smallest one, the cost will be minimized. Okay, so suppose that you have to 52 page buffer. You have to assign 50 pages for input processor, 1 page for 50 pages for input processor, 1 page for input teaching, and 1 page for output. Okay, what's the cost? page, 4,200 page transfers. We talked about this last week. If you do not remember, just go and open the slides. So now it's time for selection and projection. Okay, the next step. Selection and then projection. Okay. So what are you doing for selection or projection? Selection. What do we have? How many attributes? Multiple attribute search. Right? Multiple attribute search. So can we use this multiple attribute search? Can we get benefits from the indexes we have? Can we get benefits from the indexes we have? No,
No.
because we are gone with the indexes. No indexes is existing. So we have started with the natural join. We joined 2 tables. Now we are going through the temporary result, and we want to select. What was the indexes? We had this index on semester. Okay, we also had the index on department ID. So, what was the condition? Department ID and semester, both of them. We could use these indexes at the beginning, but now no index is available. Okay. So what we are doing is we need to scan the rows of intermediate file and then discard those ones that are not matching the condition. And then finally, you're getting the result. What is the best result? Sorry, is it? What is your suggestion? Shubeta was telling that if I were in your shoes, I would do what? I would use indexes first, refine the data, then join, right? Since we have clustered index, that can be happen, right? Anyone? Everyone follows me? So, what is the next option? Megana. What do you think about the next option? Sorry. Another technique is called pipelining. So what was pipelining in the computer architecture? What was pipelining in the computer architecture?
Series of events doing one after another in a way.
Yes, on the fly, you're doing different actions on the data and you're calculating it, right? So here, similar to that, we can use pipelining. Why? What was the burden over here? We had this amount of page transfers. Okay? For what? First we joined, then we wrote them on the disk, okay? And then we load them in this intermediate file. Then we scanned it and we selected desired records, right? Is that stupid? Yes. Why? Because when we were joining it, we could also check the conditions. So one technique could be using pipelining. So what we are doing is we can perform select a project. So what is the estimated cost of this? What is the estimated cost? Why? We just need to read it right once and then do the join, because selection and projection doesn't have any cost anymore. Why? Because as long as the records are in the memory, we are doing our actions and we are selecting and projecting. So if we assume that the output is very small, then what is the difference between using pipelining and without using pipelining? How much was it cost? 4,200 pages transfer from the beginning, okay, for the join. Then for the select and projection, you also have at least how many pages? At least 10,000 pages. Sorry, 1,000 pages. Why? Because at least the Cartesian product has the minimum number of records could be the number of the teaching records, right? So then from 5,200 pages, you will get to 4,200 page transfers. So it's a great advancement. So here is another execution plan. So I pointed to this execution plan a few moments ago, right? So what are you doing here? Sorry. What is the plan? Where is this?
First select some rows from professor table based on the department ID, then do the Cartesian product.
Exactly. So as Vanendra told, what we are doing is first we are getting benefits of the department ID's index. So we had this P+3 clustered index on department ID. So with just 2 page accesses, we can get to the first, with transferring 2 levels of, with traversing 2 levels of B+3, we can get to the first point of the CS department's professors. Then we can, since it's clustered, we can go through the pages and we can find a few professors who are teaching in the computer science department. Okay? Then what we are doing is, we will join the result with the teaching table. Finally, then we will select this records of semester fall 1994. Okay, so let's see what's the cost of this execution. As I told, since we have just 50 departments, right? How many departments we have? We have 50 departments, and it's 2 level B+3. So what we are doing is we are finding the first professor in CS department. Then, as I told, we will go through the file. So how many? We need just 2 page transfers for searching the index. We have to load the index in the file, right? And 4 page transfers to get the rows. Okay? Then what next? Why 4 page transfers?
Because the rows are spread across 4 pages.
Right, exactly. So we can have at most 4 pages for the professors. So, okay, what's the next? Again, join. So what kind of join we can use? Do we have an index on the professor ID?
Yes.
So what we are doing is we need to just go through nested block loops, nested loop join, and no, we have an index now. What is the index?
Search is for the index.
Department address.
Who told no? Panindra told no.
Say
Yeah.
department.
Why? Panindra, because already Mufika, already we have teaching. We haven't touched teaching at all. So we already can get benefits from the index we have already on teaching. We are not jumping to the rest of the execution without thinking. So what we are doing is we are getting benefits of professor ID on the teaching, and we are looping on the selected professors. Then we extract appropriate rows from the teaching table. So what is the cost? What is the cost? The index was hash index, right? The cost of accessing records and rows through a hash index was 1, right? You're not traversing any tree or anything like that. Giving to the hash function, getting to the bucket. Okay. So suppose that each professor is matching almost to 10 teaching rows. Then for 20 CS professors, we have 200 teaching records. Suppose that we have at most we will have 2. Okay, so suppose that all the indexes of the professor IDs are in the same bucket. Then we have just 1 access for each professor. Okay, 1.2 is in the worst case if we have 2 accesses and we have overflows. Multiply to how many professors? Suppose that you have 20 professors. Okay, plus 200. 200 is what?
200 rows.
200 matching from the teaching table. So, okay, so now improving with pipeline. What was the main plan? Everyone follow me? What was the main plan? Now I have to select semesters, right? Do I need to write down when I'm doing natural join? No. Why? Because already the code is in the memory. So simply I can check if the semester is matching or not. If it is matching, then output. So the selection and projection can be improved with cost of nothing using pipeline. So what is the cost? 230. What is the difference? We got from 4,200, the best case of the using pipeline with that execution plan to 230. Can I do better? Can I do better? This is the comparison from the 4,200 to 230. Okay. So we need also to have a good estimation. It's very important to estimate the size of the output of relational expressions. So we need to know how much is the output of the relational expression to choose the best plan for execution for processing queries. What was the last part? Okay, side. Okay, if you go to Sigma conference, you see that still a lot of papers are published about cost estimation, specifically when you are using NoSQL databases. Maybe I can remove this. When you use NoSQL databases, this cost estimation is getting more important because the output is very larger in that cases. So for the size estimation, we have this following measures on a simple particular instance of relationship R. So we need to know the number of tuples of R, okay, the number of blocks of R, the number of distinct values of R on this specific attribute A, the maximum value and the minimum value. Why? Here, you remember that I use this 200 pages, number of pages, number of rows, and number of the distinct values on the departments, okay, for the cost estimation of these queries, right? Here, for example, how did I get 220? Because I knew that how many professors I have, how many departments. I have 1,000 professors, 50 departments, then roughly I'll have 20 professors. How did I get 200? How did I get 200? Because I had 4 semesters and I have 1,000 pages. So roughly I will have 200 page transfers. So these are the important factors we need to. Okay. So for the estimation of the output of this simple query, what am I doing? What am I supposed to do? Everyone follows me? Remember professor's table? These numbers, how did I get those numbers? So, what is the worst case size of output?
The entire table is.
What is the worst case size of output? The whole Cartesian product. What is that? Block number of blocks of R1, number of blocks of R2, and so on. Okay. So, what is the result? Some output, right? So, the result, the number of the output to the whole thing we will call reduction factor. Okay. So, suppose that we are using, and the reduction factor is basically independent of the query by itself, and it's depending on basically the semantic of data. For example, here the reduction factor, we estimated about the reduction factor using these parameters, but reduction factor, in fact, if we have just one professor in the computer science department, the reduction factor will be this query. Suppose that we have just one professor in computer science department who taught just in 2 semesters.
That means 2 semesters.
Yes, suppose that he just taught in 2 semesters.
Yeah. 5 records?
Instead of 200, how many records I should fetch from the, how many?
10?
What?
Because there's only 1 or 20.
100, at most 100, right? So how many? 100 pages, okay? Because half of the semesters are gone. So, and what is the rest? Instead of 20, I will have just 1. It will be 101. So what will how much will be the reduction factor? 100 over 100 by 224. So this is called reduction factor of this query. If we know the result. So we can estimate this reduction factor based on the values of the values inside of the queries, inside of the relations. For example, here, suppose that we have this query, where in the query we have relationship Ri, attribute of Ri is equal to A. So how much will be the estimate for this reduction factor? What was the number of distinct values for A? Value RA, right? So suppose that we had we have 1,000 professors, 50 departments. Each department roughly
20.
what will be the reduction factor for this query?
20 professors.
Each department will have 20. What is the reduction factor? 50 over 1,000. Sorry, it's not 50 over 1,000. The reduction factor will be 1 over 50. Right? 1 over 50. This is the one from each 50 from 50 records, just one of them at least will be in the output. What is the reduction factor for conditions of RIA equal to RJB?
Professor, I don't quite follow. What are the symbols? What is RI?
Ri is relationship Ri, and A is the attribute A of that, okay? And Rj is relationship Rj, and B is the attribute of that, okay? Suppose that you have a selection query, okay? And in the selection query you have this simple condition, okay? You have this condition, you have R1 and R2, okay? Here you have R1 and R2, and you have this condition, okay? Suppose that we want to find the reduction factor of what? When the condition is A is equal, A from 1 is equal to B to B. So what is the reduction factor? How many outputs will be generated? What is the maximum? Suppose that in the teaching semester we have 20 departments, okay? In the professor's table we have 50 departments, okay? In the teaching table you have 20 just professors. In the professors table, you have 1,000 professors. What is the reduction factor?
20 by
20 by 1,000? No.
1 by 2,000.
So suppose that if I use the professor table, okay, out of 1,000 professors, one is getting out, okay. So if I use the professor's table, what is the number of the output? Oh, wait, this. What was the reduction factor? Well, the reduction factor was result, okay, to maximum of R1, right? The result is the number of the result. Okay, so we have this function, we have this condition, okay? So here in this part, we have just 20 possibilities, okay? In this part, we have 1,000 possibilities, okay? So out of, if we are in the worst case, if we are lucky, if we are not lucky,
Result by 20,000.
then
Result by 20,000.
yeah, it's just 20,000, right? So the result will be 20. Result will be not 20,000.
No, result by 20,000.
No, there is. If we are lucky, how much the result we have?
1.
20. We have 20. Suppose that we have R2 record here. 20 professors for those R2 records. Okay. How many? What is the minimum record? R2 multiplied to distinct values of R. Okay. This is one possibility. Okay. What is the other possibility?
Was that the best case?
This is the best case. Sorry, this is the best case, right? Yes. What is the other possibilities? We have R1 number of reports. Out of that, how much distinct values you have? This is Professor ID. R2. So, which one is the minimum between these two numbers? If I move this with this and this with this, it will be 1 over values R1 and A. So, which one is the minimum? The one that has?
Less records.
Yes, probably this one, because this number is maximum. So, this is also another explanation of how we compute. Assume that the values are uniformly distributed, okay? So if the numbers of tuples of the Ri is less than tuples of the number of the Rj, then for every match of Ri and matching Ri and Rj row, we will have how many tuples? The number of the tuples which is satisfying the condition will be the number of the distribution of the values of this Ri1 multiplied to the number of the tuples of Ri, the number of the over the number of the values of Ria multiplied to tuples of Rij over values of the Rjb. Okay, so the reduction factor will be maximum value. Okay, what is the maximum value minus this value? Which is should be. I'm also confused. Okay, let's do it next week. I'm also in a rush now.